The ground state energy is important because it helps to explain the uncertainty principle. In the ground state energy, you can't, the ground state energy of h bar omega, you can't extract energy from below that state. You can extract energy from above the ground state, but only because it's been placed into the ground state. So when you remove energy from above the ground state, it's because something somewhere before you removed it put the energy into it, and you can take it back out again. If I lift up this can, I'm putting energy into the state of this drink, and I can remove it by letting it go or harnessing a string to it, which will turn a little motor and light a light or make a small amount of electricity. But I'm putting energy into it so I can remove it. However, once it's at the ground state, you can't remove anything from below there, regardless that it's an enormous amount of energy, h bar omega. You know, they say enough energy below the ground state in a volume of the size of this coffee cup, this can of seltzer, to power like a major city for a month or something like that. It was huge. An enormous amount of power below enormous amount of energy below the ground state, and just even a small volume like that, let alone a large volume. However, we can't extract that energy because the Heisenberg uncertainty principle says that if we start pulling energy out from below the ground state, we would be able to localize something from below the ground state. If you think of the ground state as a well, where the very bottom is zero energy, so absolute zero, and the ground state, and imagine a U shape, yeah, and your absolute bottom is absolute zero, and then your ground state's somewhere up here at h bar omega. This energy that's in here, as soon as you pull something out, you can potentially localize something within it, because that's not energy that you placed into it. That's energy that was already there. We started at the ground state. Now, why did we start at the ground state? The reason why, if we think of living on the ground, and you can go below the ground if you dig a hole, but assuming you don't have the technology to dig a hole, you will spend your entire life at the ground level. You will have been born at the ground level. You will have lived at the ground level, been raised at the ground level. You may have gone above the ground level, climbed a mountain, but then you got your energy back when you descended. You may be able to throw something off the ground level, throw a baseball into the air, but it comes back when it lands. So all of the levels, the energy that you can introduce above the ground level in life is energy that you've added to it. So in the case of energy below the ground state, that was already there. The universe, as we exist in this universe right now, this is, I guess you could say, in a way, it's a way of saying the background radiation, the background energy of the universe is everything below h bar omega. Now, you can exclude the energy in the ground state by removing. So what is the energy in the ground state? Actually, what manifests itself? It's something called, it manifests itself through something called virtual photons. So if these, physics runs on that word, physics. So if there's something that's unmeasurable, it's no longer physics. Physics has to be something you can potentially measure. So there are certain distances that we're not capable of measuring below, for instance, the Planck length. And certain times we can't measure less than the Planck time. And certain speeds we can't measure above the speed of light. If you combine those, the speed of light, the Planck length, and the Planck time, that's your limitations of what you can uncover as a scientist. And it's not easy to measure things above that level, to measure things slightly slower than the speed of light, but it's possible. It's not easy to measure something as small as maybe just slightly longer than the Planck length, but it's conceivably possible. However, once you get below that, we don't have it. There's no way our theory cooperates with us anymore. It doesn't allow us the ability to continue to measure. So what is the energy below the ground state? Well, it's virtual photons, which are just like regular photons, except that they seem to exist for a much shorter period of time. They're measurable. These produce measurable effects. Although we can't withdraw energy out of them, you can still produce measurable effects as our energy and our matter interacts below the ground state. For instance, the Josephson junction or stiction are ways that you can interface with the Casimir force, which is a measured, reliable force, something that will produce expected results with with planned geometries. You can potentially interact with the energy below the ground state in the same way that you can interact with matter through a magnetic field. The magnetic field can do no work. Maxwell's law says that it can't do any work. However, you can use the magnetic field to change the direction of something, change the direction of the work you're doing on a liquid with the flow, or change the direction of a force that you're doing with an electric field. So by using the magnetic field, we can see very immediate and measurable effects. It's the same way with the energy below the ground state. We can't pull the energy out, but we can see the way the energy below the ground state will interact with our world, which is above the ground state. And it does it with reasonably, I mean, it requires some definitely complicated physics that I'm not very good at. I've done some of them. I've done the kind of tensors and stuff that are needed, but I don't think I really grasped it that well. It requires some really difficult calculations to really understand how to, and Feynman diagrams. You need to be a good chromodynamicist or a good field theorist to be able to figure out what's going on with matter interacting with photons below the ground state. Given that, we can intuitively understand how matter could interact with energy below the ground state. One of the explanations, obviously, is the stiction, so breaking of these cantilevers as the collection of wavelengths outside of this gap exceed the energy between the gap because it excludes wavelengths longer than the gap, and it crushes them. And that's the basis of, that instability is the basis how they make sensors for airbags. They make these tiny structures on the scale of hundreds of nanometers. And they are sensitive to small changes of acceleration because they're already pretty tensed, pretty stressed from the frequency exclusion that's going on outside of them. So it's almost like a good example might be if you put if you use a slinky and you have the slinky hanging there, and if you leave the room and you're calm, that slinky is going to just keep hanging there real motionless. But as soon as you make any movement in the air, if the house shakes a little bit, the slinky starts vibrating because it's already at a relatively when it's stationary, it's already at a relatively unstable position. And that's the way it is with these cantilevers. So if your substrate's here and your cantilever is wrapped over the top, it's already at a very unstable position because you have the force of the cantilever popping it back up while the frequency imbalance pushes it down. And it doesn't take much to be able to get this thing moving and produce a measurable frequency of movement, which can create current through various effects, thermodynamics effects, phononic effects. Thus, these photons below the ground state, although they don't exist the same as photons above the ground state, we tend to still think of them as photons, but we probably shouldn't. And the reason is the photons above the ground state are most likely macroscopic effects of interactions between photons below the ground state. So you could argue that the only real photons are photons below the ground state. And photons above the ground state, arguably, don't really exist. What we're seeing, what we're measuring, are disturbances in the energy below the ground state. Because of the uncertainty principle, we can't put energy into it or take energy out of it for very long, to the limit of physics, c Planck length, Planck time, that the ability to pump energy below the ground state has to have it removed somewhere else. And due to conservation of angular momentum and the characteristic lifetime of these virtual photons, because in a sense they're violating conservation of energy, but they're doing it for such a brief, tiny period of time that it's physical. We have no problem with it. And we renormalize these things, and there's a conflict about that. I'm not going to get into it because I don't understand it well enough anyway. But renormalization is a form of this, where we have these relatively large energies that we have to account for. Mathematically, the way we account for them is pretty simple. We brush them under the rug. We get the day's work done. We go home, and then we drink, and we think about the problem, and we start again the next day. But we just drink seltzer water. We don't drink tequila. We don't drink any tequila. We don't drink gin with quinine water mixed with it and thin slices of lime. We don't drink that. We just drink seltzer water. And there is seltzer inside this can. I opened it fresh. I'm not like sneaking beer into a seltzer container. That would be like not healthy for me. So we get on with these problems with renormalization because it turns out in the end we take measurements and we're fine. Our bizarre mathematical exuberances work. They produce values that we can measure and that agree with prediction. But if you think of photons if you think of our classic definition of what a photon is and what light is, if you think of it as a macroscopic measurement of energy going below the ground state and then extracting itself so as not to violate the uncertainty principle, that could be another way of thinking of light and of thinking of photons. And that all photons may be these incredibly short-lived bursts of energy that only exist in the universe to not violate thermodynamics and to not violate the uncertainty principle. Like we think of photons and we think of energy as being this thing that has to obey uncertainty, that has to obey a particle's momentum. We think of these things that have to obey the second and the third law of thermodynamics. We think of these things that have to obey the Lorentz force law. We think of these things, but maybe a better way of thinking them isn't as things that have to obey, but rather the very definition of them, the reason they exist within every single parameter that they can minimize, optimize, least actionize, if you want to take the classical mechanics approach of least action being the mode that a system will take, while always increasing the entropy, of course, is that these particles will do the least possible amount that they possibly can to still abide by the laws of thermodynamics, to still abide by the uncertainty principle, to still abide by Maxwell's law. They'll do whatever they can. So they're not particles that also obey those laws. They are the physical manifestation of those laws. The laws are more real, more accessible, more impactful in our lives than those particles. The particles, in a way, don't even exist. They're the laws interacting with nature. They're the laws restricting nature, and like a balloon, they're squeezing one end so that the other end can pop out. You know, squeezing a half-dead balloon so that you can have high pressure in the other end. So that when you turn on the flashlight and you have the last little dying embers of that bulb, as your battery's nearly dead, not an LED bulb, but say an incandescent, where you have a more linear approach rather than just on and off, like with a diode, because that's a semiconductor and there's essentially a form of gate in there. But think of a small incandescent bulb that's just about to die out, and you have a few last photons coming off of it, that those last little gasps of photon before the light goes cold completely and emits no more photons of any meaningful wavelength, that they enter the ground state. The ground state says, get out of here. We have to obey the uncertainty principle. Get out of here. We have to obey conservation of energy. Get out of here. We have to obey thermodynamics. So then they pass them off, one virtual photon to the next. And virtual photons don't live very long. They live the Planck length no longer than the Planck length divided by the speed of light, which is pretty tiny. I can't do the math right now, but it's short. It's really short. They can't live too much longer than that. But during that time, during that brief existence in the universe, these little virtual photons are grabbing that energy and trying to get rid of it like a game of hot potato. And they're conserving angular momentum so it doesn't spread much, continues with correct linear momentum. And then eventually, when the virtual photons can interact with something that has empty space inside of it, empty space being the lack of vacuum energy, the lack of energy below the ground state, because to have energy below the ground state, you have to have a vacuum. And if you have a dense enough material that excludes a sufficient amount of vacuum, you have very little vacuum energy. The vacuum energy exists when you don't have a tremendous amount of energy above it. When you have a very massive item that presents a rather high step potential and your energy exponentially decays as it tunnels through it, this massive block over here tends to exclude a lot of that below ground state energy. So you essentially have something which, although to us seems to be very solid and rigid, in the world of energy, it's this vacuous open space because there's no vacuum energy inside of it, very little vacuum energy inside of it, increasingly less vacuum energy inside of it as you go denser and denser, and you're farther and farther away from the mass defect of nickel and iron. So when it excludes that vacuum energy, and then these virtual photons are playing this game of hot potato with some energy that you imparted into it, that last little dying gasp of your tiny incandescent bulb and your nearly dead flashlight, and they're throwing it off, and they come upon something that has empty space inside of it, something massive that's filled with empty space, that's not filled with a vacuum, they dump it out because they want to adhere to the uncertainty principle. They want to adhere to the laws of thermodynamics. They want to adhere to Maxwell's laws. They want to adhere to all this stuff. They follow, these particles are defined by their slavish devotion to the laws of nature. So they dump the energy out into this empty space. This is not a great example because it's filled with liquid, but it probably has half empty space, half vacuum space in it. And that's when you start getting your Weinberg's photon interactions with matter. That's when you start getting into this real complicated physics that relies on field theory and chromodynamics and solid state physics, and it gets really complicated. But what happened between those 2 points, the matter at the little end of your flashlight, the little ember in your flashlight, and the matter as the flashlight shot through space to hit this can, that's where some interesting physics is happening. And that's what, as a field of physicists, we've had a really hard time describing it. We can measure certain things with ease, and yet we have no idea how they work. It's wonderful in a sense because, you know, we live in this world where we have phones that have computers inside of them and delicious seltzer water. We have all of these modern technologies, abilities. We have the ability to understand Schrodinger's equation and why that happens. We live in a time where we can do covariant analysis and actually come up with a reasonably good prediction to the perihelion shift of Mercury. Remarkable times, unbelievable times. And yet, there's something incredibly reassuring and beautiful that we don't have it yet, and that we might never have it. And then as soon as we get that, there's going to be something else we don't get. Yeah. Oh, okay. Look, this is a big one. Okay. This is for 4x7 people. Okay, this little thing here is a fix-it clip. I know I've shown this on previous ones, but the utility of this device keeps becoming more and more apparent. And I really need to get this going for the 4x7 users. I know I've promised this thing to you for about a month and a half, perhaps. I just don't have the time to really get together a clear marketing direction on this. How useful does it be? So I think what I'm going to do is give you what I have and let you guys deal with it. This is an easy enough think of this as the Russian tortoise of pets. As long as you don't let it out in the backyard and let it get lost, this one will, and you just give it some lettuce now and then, this one will survive. You will be able to figure out how to get this thing to market and move a ton of these things because it's just so useful. People, you ask somebody, you know, when people need stuff, they always have a knife with them. They always seem to have a blade with them. They always have something on their keychain that'll pop off a bottle opener. They always seem to have that. Yep. What is the thing you need more than almost all the time between a metal device? More often, we can cut things. We can always figure something out. We can gouge in with our fingernails. There's always some way we can solve that problem. We can even, I mean, I've opened enough boxes with just the key to a door or a car. I know I'm not supposed to, but it works. However, the ability to fasten two materials together with rubber bands, duct tape, thread, needle, this seems to be something we need more often than the ability to cut it apart. I suspect it has perhaps an entropic reason because the universe tends towards greater entropy, and having things come apart is a more common entropic position than having things come together. You have to put energy into things to bring them together. You don't have to put as much energy into things to make more disorder. That gives you energy. That disorder produces energy for you. Creating more order, decreasing entropy requires work be put into the system. And I think that's why you end up needing tape a lot more than you end up needing blades. So this is a great little 4x7 product. I love it. I've just been using it so much. It's been one of my favorite 4x7 test units. And there's just so much flexibility with this in color, in branding possibilities and variations of it. We're having different tools on it, always under the fix-it clip umbrella. And it's a amenable product for us to protect the intellectual property which the 4x7 backers essentially inherit. Is really the best way to describe it. It's kind of sort of an inheritance more than anything else. Okay, well, my key ring is irreparably bent. I believe that's it. Thank you. have a good, oh, wait, this is important. Okay. I did a little thing the other day. I had one very ambitious goal, and that was for cPanel. Yeah, that was for cPanel. Is that backwards? Well, that would be backwards. Although that looks frontwards to me. So I guess it must be like that. There we go. Okay. So I have one ambitious goal for this. And the ambitious goal is within a certain amount of time. I don't know how long that's going to take me. Why rush it? You don't need to put time constraints on you. You just work toward doing it. Within a certain amount of time, I want everyone in the world who needs access to clean water to be able to have access to some variation of cPanel. There is about 7 different variations of cPanel technologies. And all of them have different applications. I would like to get the cheapest one down to like $1 or $2. It's possible. I really believe that. I think it's possible. I don't know, exactly where generally as something costs more, it tends to last longer and you get more water out of it. It interfaces with the sun better. It's not as fragile. There's some optimization points for solar desalination technology, but I believe that there's also a sweet spot for all these different technologies. And that's my little pitch, is these guys, which is me too, will have some sweet solar desalination all over the world. So there's a little kid living in Haiti who has diarrhea, and his mom just like slaps out a cPanel, dumps some contaminated water in there, lets the sun do its job. A day later, gluck, gluck, gluck. Hey, dude. Hey, diarrhea kid. Here's some nice clean water. Oh, thanks, Mom. Maybe add a little Kool-Aid in there, sugar if she can get it. Then cut it with some more water so it keeps getting more and more less concentrated. The kid doesn't know, as long as it's still a little pink. Little kid in Haiti's like, gee, thanks, Mom. Oh, yeah. We have to get the Kool-Aid, dude. All right. That's the auspicious goal. cPanels for everybody. I mean, ultimately, look, it's like a piece of saran wrap. If you do it right, if you can find a way to make it work, is a great cPanel. It does the job. It just does the job. It doesn't last long because this stuff is not UV stabilized. You put that stuff out in the sunlight and the UV attacks it right away, makes it brittle, falls apart, dries out. But as long as it's not attacked by UV light, it lasts a long time. Unfortunately, for solar desalination, the only way you can make it work is you have to couple all that UV light. So when you're using plastics, you need to find plastics that are not broken down by the UV light. With the UV light, it starts breaking molecular bonds, I think hydrogen bonds, within those hydrocarbon molecules. So you have to find other stuff. Some people just use glass. Glass is really heavy. Glass also is difficult to work with. Plastic is a miracle technology, which unfortunately has generated bad press because it's so ubiquitous, it ends up out in the ocean, and then it gets stuck in the nostril of a sea tortoise, and that makes the whole plastic industry look bad. But nobody really pays much attention to the garbage disposal industry that got it there in the first place. Instead, we just blame the plastics industry. Well, the plastics industry has saved millions of lives by allowing water to be transported with remarkable efficiency, by allowing solar disinfection, by allowing food and medicines to be stored stably, inexpensively, and energy efficiently. We just need to find a way, and recycling plastics is possible, but the difficulty is that there's so many different kinds of plastic. Once you mix them, And as I was talking to a father of a friend of mine, father of a friend of my son's, many plastics, after you melt them, they no longer have the same molecular characteristics. They no longer amorphosize the same way. So plastics don't like to be reformed. And when you mix them, they don't necessarily even have very different densities. If you mix metals, you can melt them out and separate them that way, but you can't really do that with plastics. They just don't really come apart. It's like trying to, with different plastics, it's like mixing flour and sugar and then expecting to get them apart again. As you mix it more, it becomes more and more impossible to get the flour and the sugar apart. They don't separate the way oil and water does. So in the case of plastics, what we really need are products and industries that can make functional and useful devices and useful ways of increasing wealth and health and happiness with mixed plastics. The one I've seen that I really liked was, and I believe it's made with mixed plastics, is this flooring material for basketball courts. Some of it is like a chipped up stuff, and the other is a hard plastic like substrate. And I believe that's made with compressed plastic. So that's what we need more of. We need more, and we need that technology needs to be available. It needs to be available on a light manufacturing basis. If the only way you can make stuff, the only way you can make these little bricks is out of wildly complex, high compression, high temperature, expensive devices, then it's going to be difficult. If we can make these plastic devices out of mixed plastic, like if you have a big bag of old shopping bags, and you have a big thing of old water bottles, and if you can melt them just enough so it doesn't create a lot of vapors, or even just compress them enough so that it starts leaching some, or maybe even adding a little bit of solvent to it, so that you can make something coherent out of this, something you can use, then plastics can start integrating in our lives in a much better way. There's nothing necessarily evil about it. They make fantastic pots to plant flowers. Plastics make great containers to hold water, to hold irrigation water. They make wonderful things to use in the outdoors. You can line ditches with them. There's not all plastics leach toxic materials. Some are very stable. Okay, thank you.